University of Notre Dame. He barely needs introduction because most of you were here Wednesday morning when the details of his life were revealed to you, but mainly we think of him as the student of the lunar Apollo sample return rocks, and he's served as chair of things like the Lunar Access Group, LEAG, and has told us to come back this morning to hear the rest of his story. Clive, Neal.
Thank you. Thanks very much. All right, let's see if this works. There was some connectivity issues before, and there still are. So this is going to be interesting if there are no slides. But I'm a professor, I can talk for 40 minutes without slides. So I wanted to talk to you a little bit today about the possibilities again. I mentioned that on Wednesday. But listening to some of the talks yesterday and the fundamental processes that are being studied, I want to try and put those in some sort of perspective from what the moon actually can offer. And Alan talked about the lunar economy, the fact that students can go to the moon in the not too distant future to go work there. As I said, I don't think that's science fiction anymore. I think that's science fact. And maybe it will be fiction with my slides. Oh, well, anyway. So what I wanted to do is to talk to you about a couple of documents. One that is a living document, that's the Lunar Exploration Analysis Group Lunar Exploration Roadmap. When I was chair the first time, we were charged by the NASA Advisory Council to put together a roadmap to go to the moon. And we took that seriously because it took 4 years to put together, and by the time we'd done it, we were going to an asteroid. Then we were going to bring the asteroid to put around the moon. Then we were going to bring a 5-meter boulder to put in orbit around the moon and send humans to explore it. Then it was a 1-meter boulder. And the question came back, well, what is the point of that? Now we're going back to the moon. There's a bigger boulder just below the one they were going to orbit that is very good for science. It is very good for the opportunities that this community can have once the Artemis Base Camp is up and running, and that we have some sort of support structure there so that the fundamental experiments that need to be done in physics, fluid mechanics, life sciences can be conducted such that we know how to go further into the solar system. And, all right, are they coming up or are they not coming up? Doesn't look like they're coming up. All right, well, I'll keep going. So the basic tenet is, when we put this together, is that we did have this community well represented. And there is a whole section in this roadmap that is important for this community to look at because it represents opportunities. And the National Space Council, when it was reformed, actually used this as the United States Lunar Exploration Roadmap. And they took notice of it. And I am hopeful that this new Space Council will do the same because it is comprehensive, it is inclusive, and it represents a lot of opportunities of aspirations of where we want to go and what we want to do. And 1/3 of it is, how do we use the moon to go to Mars? How do we learn to live and work productively and successfully off planet close by so that we can go do it much, much further away? Well, one thing that the moon does offer, and we know this now from not only Apollo data, but post-Apollo data through the 90s and into this century. With all the orbital flights that have been going, we now know that there are resources on the moon. And those resources, everybody's looking at and going, you can't touch them, they're for science. Well, we want to mine them. And as soon as you use that M word, scientists get upset. You're going to ruin, you're going to trash the environment. Okay? Just by landing on the moon, the rocket exhaust is going to get caught in cold traps, and you are not going to be able to see the biosignatures. Okay, well, if that's true, and you're at 35 Kelvin, all those volatiles are going to be at the surface. If you look at the estimates for micrometeorite guarding of the top couple of centimeters, it's 50,000 years to actually mix it in the top couple of centimeters. So we need to use our science to understand how we're going to damage the environment, but then how we can move forward together to not only access those volatile deposits for science, but also to enable human sustainability on the moon. So if we look at the data that's come back, we sort of know where to go. And Tony Colaprete gave a talk on Wednesday about Viper, the Pathfinder, as he described it. If you look at the way we do prospecting on this planet, it's not a mission. There's not one field season to go out and look, it's a campaign. We need a prospecting campaign on the moon to actually figure out what form is this in, how much is there,
I'm good with those.
what is the grade over distance,
And
to actually talk about reserves. And everybody talks about resources. NASA talks about resources all the time. Resources on the moon. We've got millions of tons of water ice on the moon. It's a resource. Now, in geology speak, it's not a reserve. And there's a big difference, because reserve brings in economics. Economics brings in commercial people. And we have a chicken and egg thing going on right now with everybody saying about resources. Well, we need the mining companies involved. Mining companies will not get involved with the moon and lunar resources because there's no market. How much are you willing to pay to get the stuff out? There's only one price point from United Launch Alliance of about $500 a kilogram. And that's not going to think of what you've got to do. If you look at Shackleton Crater, and Shackleton Crater is right at the south pole of the moon. It's got a nice signature of water ice in there. And that's really good. But it's 4.5 kilometers deep, 30 to 40 Kelvin average temperature year round, and it's down a 30-degree slope. So how can you access it to get those out? And how do you then keep machinery and keep the or the infrastructure alive? But there are other places to go. We know that. The trouble is, Lunar Reconnaissance Orbiter's data set is biased towards the South Pole. So the South Pole looks really good despite all these deep craters with steep slopes. And the North Pole not so good because it's much higher above the North Pole. But there are craters at the North Pole, Earth-facing, that are partially permanently shadowed that you can land in and investigate. You don't have to go down a slope, and you can land in sunlight. And you can traverse into the crater. So if Viper misses its launch window, maybe, oh, look at that. All right, I'll start again then. All right. So which one do I use now? The green button. There we go. All right, so we'll go through all of this. All right, I get an extra 20 minutes, right? So again, looking at these resources and are they reserves, I just want to touch on this point because we can divide resources that will be useful in situ on the moon and those for potential export. And the ones that potential export: rocket fuel, water ice. Now, when I was a lad, the moon was bone dry, although bones are quite aqueous, but we won't go there. But the moon was bone dry, and then all of a sudden, Lunar Prospector in the 90s showed neutron suppression. Now, hydrogen absorbs neutrons, and it was over both poles, and it then connected with the theory that was published in the 60s that these craters at the poles of the moon would contain water. Platinum group metals. Now, I'm not a believer of this yet, but have you seen the price of platinum group metals? Holy moly, they're expensive. And then rare earth element deposits. We know we have a prosolarum creep terrain. Creep is potassium, rare earth elements, and phosphorus in the central near side of the moon. And we know that rare earth elements are becoming a hot commodity down here with all the electric cars. And then we get helium-3, which is a future potential export, because this is the nirvana of fusion. Aneutronic fusion, no toxic byproducts. Harrison Schmitt, Apollo 17 astronaut's a big fan of this. And in his book, Return to the Moon, he calculates that one shuttle cargo bay full of helium-3 would fuel the United States for 1 year. There's money to be made, but we're not investing in the tech. Other countries are. Could I say China? Oh, I said it. Korea? They are investing in fusion technology and making great progress in the last 5 years, gone from less than a minute to multi-minute sustainable fusion reactions. This is becoming a reality. China has actually produced helium-3 maps of their 2 orbiter missions to the moon, Chang'e 1, Chang'e 2. I don't believe them, but they've produced them. We need ground truth now to figure out if they're real. But there's potential there, but maybe the one reserve that we have is regolith and getting oxygen. And there's several talks at this meeting about, well, we've got the regolith. We can get oxygen out of it no matter where we go. We've got the Mare regions or the volcanic regions, and we've got the highland regions, but all that regolith contains about 40% oxygen, plus metals. So by extracting the oxygen, we then create the metals. We have a resource, an in situ resource. We don't want to take titanium with us. Why would we? A lot of titanium on the moon. But that theory about polar volatiles was actually confirmed with the LCROSS mission. Tony Colaprete was the project scientist for that as well. Tony and lunar water go, well, back a little way, not way back. But this is our 1 point of ground truth, about 5.5, 5.6, plus or minus of 50%, that was actually measured by that plume that came up within that impact. That's one data point. But then we have Shuai Li's work looking at integrating multiple data sets. So rather than one data set, there are now multiple data sets all pointing to the same thing. There is water ice at the surface of a lot of these craters. At the surface, we get reflections from LOLA, the Lunar Orbiter Laser Altimeter. Much enhanced reflections to show that they're coming off a reflective surface, interpreted as water ice. You look at some of the reflectance data that they managed to get back, there's this water signature in those reflectance data. You have to do some manipulation in order to get those data, and if anybody's going to manipulate it, Shuai Li's going to do that. And again, up to 38% at the surface, and if you then overlap that on the neutron maps, neutron suppressions mean that you're now integrating that water over the top meter or two. So it's not just at the surface, it's at depth as well. And again, given the pixels up to 10 kilometers per pixel, it's, we need to get down to the surface to actually get some granularity to those data. But this is an interesting one. Craters actually conform pretty well. Depth to diameter ratio is well known. But if you look at a lot of the south polar craters, they're much shallower than they should be. It's been hypothesized that up to 10 meters shallower due to the presence of water ice. It's a good model. It needs to be tested. It's still a resource. This is not a reserve. And that's the point, is that we need to look at that, because the potential for a market is not in life support consumables. It's in fuel. Sounds familiar, doesn't it? And you can see there that rocket fuel, water is the oil of the solar system if you build the right engines. Sorry, SpaceX. I always have a friend at SpaceX, and every time I see him, I just shake my head and say, got the wrong engine. No methane on the moon. There's water everywhere. And then Viper becomes this first step in prospecting, this first step to go and figure out the reserve potential, to actually add fuel, if you like, to the cislunar economy. This is critical. We need to know the reserve potential, because those data will inform science. Viper is a science mission director at mission. It's going to inform the science. But if you think about what we need to do then, once we figure out the science and once we figure out the data, we know the reserve potential, we know that it's big, then how are we going to store these products? Cryogenic fluid management becomes very, very important, but we need to know what's there. Outer Space Treaty and Moon Agreement tend to forbid nations going and looking for and utilizing resources. If we had an international lunar resource prospecting campaign, that gets around that issue, and the data that comes back for all society down here is enabling. This is something that I think is important. I've talked to several people. We talked to Australia, talked to the European Space Agency, talked to some people in Canada. They really like this idea of an international lunar resource prospecting campaign to actually fuel, again, the economy, but also the research that needs to be with that as we move forward. All right, how do we go back? Let's try that one. There we go. So a couple of calculations based upon ISS consumable data. As I said, life support consumables are not going to give you a business case. Artemis Base Camp, you can see number of days there, 3 months, pretty much, and then oxygen needed with a different number of astronauts, just based upon the average intake from space station, and then water also. But this comes from the NASA's plan for sustainable lunar exploration and development, came out in 2020. And again, the definition of sustainable. We started to hear some today. It's the first question I asked when this came out, when we had a meeting. I said, what's your definition of sustainable? Within our budget. Okay, fair enough. We need to do better than that. If we look again at this document, transportation systems come in. LOX hydrogen transportation system. Gotta love Blue Origin for that. LOX hydrogen. Not putting CO2 into the atmosphere when it launches off this planet. Yeah, water's a greenhouse gas. But we know how to use that. So reusable engines, and you can see the reason why, and then we get into the zero boil-off issue. How do we store it? Well, you don't store hydrogen and oxygen off planet, you store water, and you crack it when you need it. I'm a geologist, that makes sense to me, but somebody needs to prove me wrong. And we got a methane problem. You have another process. You have to bring carbon with you or mine the regolith to get solar wind implanted carbon out of the moon's regolith and then create your methane. It can be done. And if you look at Mars, well, there's been methane found in the atmosphere, but it's minuscule. So you have to take the carbon dioxide And this is what MOXIE is doing on Mars 2020. Extracting oxygen, you've got the carbon, but then you have to make your methane. So you have to crack water, use the hydrogen there to make the methane. So it can be done, but there's more processes, more machinery, more infrastructure, more things to break. So cryogenic fluid management becomes critical in an off-world setting, in microgravity, in partial gravity. Store those cryogenic fluids in permanently shadowed regions of the moon. Get them out of the sun. One way to do it. Again, Shackleton Crater. I already talked about that. As it looks like a good resource. It's unclear if it's a reserve, despite how much is in there. So we really need focus on these issues, and I learned a lot this week by coming here and sitting here. I heard Michael Meyer talk yesterday. Holy crap, that's really cool. And I really enjoyed that, because it gives me hope with what is going on here, that we have the technology close at hand to be able to harness the reserves once we figure out we have reserves on the moon. So again, I went into this. Economics plays into reserves. Economics is something that will allow industry to participate. It'll open up a whole new sector of our economy, just as, low Earth orbit has. Alan was talking about nanoracks and other companies that are going from strength to strength just in, 20, 25 years? I mean, look at that, 25 years. And those of you under 30, it goes quickly. So, but that's the point. We're in that chicken and egg thing. What's the market? What's the market for these products? This is something that space agencies can foster. If we would commit to human permanence on the moon, rather than a sustained presence, because that is very wishy-washy, doesn't engender confidence. If we had a human permanence on the moon, that would then give companies the safety, if you like, that we're in it for the long game. We're in it for the long term, and something that's going to take 20 years to sort of return on investment can happen, but we need to start now. And I really think it starts with this international lunar resource prospecting campaign, because resources do not equal reserves. The term resource has been used when we mean reserves, and we don't know, maybe regolith. It's the only reserve we have on the moon, maybe. So I want to end up with this. This is the Lunar Exploration Roadmap. So we have goals, themes, goals, objectives, and investigations. And we've got science, feed forward to other destinations, and sustainability. Sustainability, you can return on investment. If we don't show a return on investment to society down here, it'll be a government-funded program that gets cancelled. Can it be self-sufficient? Certainly not at the beginning, but look at low Earth orbit. Look at the changing landscape of launch. A changing landscape, to me, is a lesson from history. So I want to point out to this audience, the one at the bottom here, Psi-D. And this is the one where we assume that we have some sort of permanent habitat with some sort of lab space. And again, combustion and fundamental physics. There are four objectives, 14 investigations actually outlined in the Lunar Exploration Roadmap for this. There are many more. This is a living document. If there are others, email me. We'll get them in there. It's a living document. This is not the end. This is the beginning of a process. It has already been updated 3 times, and it will be updated again based upon new data. And again, fundamental physics. I talked a little bit about that on Wednesday. Way out of my depth on that one. But I realize it's important, and I know a little bit to be dangerous. If we then look at fluid physics, we found 4 objectives with 11 investigations there. I'm not going to go through them all, but these are the opportunities that we found when we went through it. This is what the moon can do. This is what we need to know, because this fundamental research is important for creating the cislunar economy. We then look at mineral processing. Again, if we're going to process regolith, now how are we going to do this? We're in 16G. We're not in 1G. We know how to do it down here. We're in a vacuum, an electrostatic environment that is very, very different from down here. But again, there are 3 objectives with 5 investigations noted under this particular topic. Then we get to life sciences. Well, 10 objectives, 27 investigations. Microbes, humans, plants, and it goes on and on and on. And I've just given a summary here and morphed things together. I'm not going to go through it, but I put the words up to show you that we spent time going through this with experts in this field to make sure this was included, because it is important. Can we actually stop the skeleton from dissolving in microgravity? If we can, have we cured osteoporosis? Is 16G the sweet spot to stop that? We have no long-term data of humans on the moon. Is that going to be enabling for getting humans to Mars and having them be productive when they get there? Lots of questions. So all this research that I've gone through is going to enable humans to survive and thrive off planet. It's fundamental, but it's necessary, but it has a very, very applied goal. So Alan talked about the Commercial Lunar Payload Services Program, which is delayed. And again, it represents another exciting opportunity. I spoke with Dan Hedrickson on Wednesday from Astrobotic. I've known Dan since he joined the company, and I said, so, you're going to land successfully, right? Oh, yeah. I said, make sure you do. No pressure, but make sure you do. This is going to enable so much more, and this community needs to look at the calls that come out through the Science Mission Directorate to get payloads on there, to start doing some of those things that I noted in the Lunar Exploration Roadmap. At least make a start with some of those investigations. And you could refer to the Lunar Exploration Roadmap as a supporting document in those proposals. So you can see where they're going now, a rate of 2 per year. That's the cadence. Once they start, it's 2 per year, 2 per year. Sometimes 3, because Viper, Astrobotic's carrying Viper. Going to the moon. So, it's a world of opportunity out there. This community can not only help humans survive and thrive on the moon and Mars, but it can enable a cislunar economy. By working together with people like myself, geologists doing the prospecting campaign, business people, lawyers, we can make this happen. So what we see is going to the moon is being inclusive, and it's inter and multidisciplinary. And we all work together to get it done. Really, really important that we all work together to get it done. So with that, if there's any questions or I have time, thank you very much. And thanks to the AV guys for getting the slides up. I know it was a pain in the rectum.
Yeah, that turned out to be quite a challenge. I think we have time for just one question, and Here's one. How will we need to change our approach for mining if the water on the moon is more of a muddy dirt than dirty water?
Okay, well, if you look at the LCROSS results, we already know it's not pure water ice. We know that. So we need refining capabilities and infrastructure. We know that now. But how much of that 5.5 weight% water is around? Does it go up to 30 weight%, such as Shui Li is saying at the surface? Does that go down a foot? Does it go down a meter? How widespread? What area is that? We don't know. This is why VIPER is an important first step, because it's testing the system that can do the prospecting, the grid prospecting, if you like. So we understand, okay, go a meter this way, it's now 10 weight%. I go another meter, it's 20. I go another meter, oh, it's back down to 10. We've got to understand this, because those neutron pixels, 10 kilometers, which is a lot better than Lunar Prospector, that's on LRO, the LEND instrument. So we have to understand this, and it's expensive. If we went together as an international lunar resource prospecting campaign with commercial companies, we go together. Isn't that what the Apollo astronauts said? We go together with all mankind, or for all mankind, or humankind. I mean, that's the point. What Apollo taught us was competition does not give you an enduring space program. I do not want to see a space race with China, because that will not end well. If we have something like ISS where we have collaboration and cooperation, 20 years and counting. Learn from history, otherwise we will repeat it.
Thank you very much, Dr. Neal. I've asked John Kiss to introduce